Oh, maybe not.
There we go. Alright.
Go ahead.
Yeah, so anyway, it's not, I haven't actually got anything about something to talk about because I'm really here just to get advice on what it is I should be doing. I have done simulations, not just analytical stuff, but it's been kind of one-dimensional and not two-dimensional, but linearized, so much easier to work with. And yeah, so I'm going to talk about the problem I'm working on and what I've done so far, and hopefully someone can tell me the best way to approach it from this point. So I'm working on a property of superregulation. So it's this pattern that you can see here. And it's solar patterns. They've got a typical cell size of 1.6 times 10⁴ kilometers, and they last for about a day. And they kind of flow outward from the center, and they're convective looking, but there's some questions about what's actually going on there as well. But my real problem is that they've been observed to rotate faster than the plasma. So I'm trying to explain this, the fact that plasma is moving along, and this pattern on top of the plasma is moving along but faster than the plasma itself. And so there's been an observation that they don't just move faster, but they also have wave properties, and so they've got a phase speed of about 65 meters per second. And so there's controversy about this, that there are these observations. It was suggested that maybe it's the Coriolis force that's causing this. Other people have suggested that it's not really a wave after all. It kind of looks like a wave, but it's really bulk motions of various sizes moving in different directions, and that might trick you into thinking it's a wave, but really it's not. And so we're working on the assumption that there's this, we know that there's a steep subsurface shear gradient underneath the surface of the sun, and our explanation is that this is what's causing kind of unstable conductive modes to turn into running waves, and that's what we're observing when we see the superconduction pattern. And so our goal was to take this and model it, and thus compare the resulting phase speeds with the observations to see if it could reproduce the observations. So we're using a formulation that was done back in the day with analytical analysis that showed that this phase speeds for these unstable modes should be between the minimum and maximum of the shear flow. So that's between 0 and 65, according to the new seismology data that we have. And so we're looking at a situation in which we've got an unstable layer bounded above and below by stable layers, and then a shear profile that is going along just in the x direction. We're only looking at a two-dimensional model right now. And so obviously it was idealized that diffusivity and viscosity were ignored, and we have to have these stable regions bounding it. But these kind of are unreasonable for the kind of scale that we're looking at. And so we've got equations that are derived from the linearized equations of continuity, motion, and adiabatic compressibility. And we're looking at them in terms of pressure perturbation, vertical displacement. And so we're considering both of these things to be wave-like, right? They're periodic functions in the horizontal coordinates and time, so we're only really looking at some unknown variation in depth. And we have a bunch of parameters that also vary in depth, and we got these from the noise seismology, so we have some data to put in. So we started with these equations, I guess. And we got both final equations here that we're looking at. So we've got the frequencies omega and the wave numbers k, so we're trying to get a dispersion relation, so we're solving for frequencies at a series of numbers of values of wave number.
So what is Q? The variable Q?
Q was the vertical displacement.
So you have, but you should have 5 equations, right?
Yeah.
Right.
We had these.
X, Y, Z.
Right.
X, Y, and Q, that is, and then you have
We have
rho and P, right?
yeah. So
Right.
we've combined them together and eliminated certain values and done a transformation to get displacement rather than velocity. And so we combined them together to just the two equations that we're looking at. And I actually later want to go back to these original equations because magically they're easier to modify than this here that's all combined together. So at the moment we've got this, we're going to end up with an eigenvalue problem in terms of these omegas, but we've got squares going on, so we end up with a polynomial eigenvalue problem, and if I'd stuck with the original one, then we just end up with the regular eigenvalue problem. So it ends up being the same thing, just slightly different location. So this is the verticell frequency, and it got it from human seismology. It's the one that kind of has the biggest impact on the results, in that depending on where we put our upper gravity condition, you can end up with modes that kind of get caught in that steep increase there, and you end up with kind of a much smaller scale than we're interested in. So we have to be careful about the exact boundary because of this particular coefficient here. So without any shear velocity, if we just have that set to 0, we end up with these real P and F nodes and entirely imaginary convective nodes. And so convective nodes are the ones we're interested in, and this is the shear velocity that we're getting from helioseismology.
So the growth rates, they only order of what, 5 minutes, yeah? Or much shorter? The imaginary varies in
yes.
parts of the eigenvalues. It has it in microhertz.
Yeah.
Yeah, huh? Okay. Think about it. Much longer than 5 minutes. 5 minutes is what?
3 millimeters.
So it's very slow then, yes.
Yeah.
At which depth was that then?
What do you mean by that?
This is a function, it's not a function, depth, no.
Yeah, these are,
Or depth.
yeah, the depth appears in the other functions.
Oh, by the way, plus and minus. Yeah, so if decaying and also,
Right.
of course, exponential
So,
increase
yeah.
amount.
We're really only interested in the ones that grow, because
Yes.
decaying operation.
Yes.
So once we have this in, then the other stuff stays pretty much the same, but we end up with these kind of real components, real parts to the convective modes. And those correspond to phase speeds that we've subtracted the surface speed at this point, so this is how much faster they're going than the surface. And so we get up to 26 meters per second, but if you recall, observations were 65, so we're encouraged by this because it indicates that we're not entirely on the wrong track here, we're getting the same order, but there's still a gap there that we need to explain.
You mean because it's simply not 65?
Right, that it's not as fast as the observation, so we haven't entirely explained it, something else has to be going on as well. And so we thought that maybe, helioseismology isn't just, it's not entirely accurate, we could be slightly off on the shear gradient, but when we tried it with some different values of shear gradient, it increases a bit, but it doesn't increase fast enough for that to really be the explanation that some small error there is causing this difference in the observations. And so these are the pressure perturbation functions in depth. And you can see that most of the oscillation is kind of above that dotted line. That dotted line is the depth of the shear velocity at which 65 meters per second to match the oscillations. So seeing these, it's not really too surprising that we're not getting speeds that fast, since most of the variations happening right at the top of the layer. And so this is what the perturbation functions look like without the shear flow. And then when we add the shear flow, we get kind of this change to it. And this is part of our argument that we're not just seeing convection, that there actually is wave-like behavior going on here, because otherwise we'd expect to just have these functions again but have them be moving. And so we also considered the case for the polytrope, and this was the verticell frequency again. And it doesn't have nearly as much of a drop right near the surface. So first 3 convective modes, and they correspond to much higher phase speeds. And I didn't include those, but those functions that I've just seen, they kind of penetrate deeper into the layer, so we thought from this that maybe whatever we're doing with our model might be artificially constraining the modes to higher up in the layer than they should be, and that could be part of the difference. So we've also considered the Coriolis force as part of the explanation, and we've used we've got some results for someone else's simulations, and unfortunately they weren't really quite in the right range of wave number that because of the sampling interval, but we only got wave numbers between -20 and 20, and we were kind of hoping for bigger than that, so we could only really get kind of an indication from these. And so we had kind of a ridge around 0, which you expect from the rotation. And it looks like that's all there is, but really there's higher ridges there that are just so much less dominant than that main one that you can't see it. But they look to be pretty much vertical, which would suggest that they're just kind of infection rather than waves. And of course this doesn't really mean anything because, once again, they weren't really quite for the right wave number anyway. But
So you said K was 20. What was it K in the previous?
we had between
It's
50
shaded.
and 150.
Between what?
50 and 150.
Yes. Okay.
And so we wanted to, so we thought this meant that, the Coriolis force wasn't doing it. But we wanted to check to be sure, so we modified our original equations and added these new Coriolis force terms. And it did have a bit of effect because you can see that we've got phase speeds that are a bit higher than we had before. The red ones are with this Coriolis force and the blue ones were the original ones. But it's pretty small compared to the size, so therefore has a minimal effect at best. So we also considered adding a toroidal field, and you can see there this is the phase speed as a function of this constant field that we did put. That for low values it doesn't do anything at all. There's kind of a range in which it causes an increase in the phase speed, and above a certain point it completely destroys convective modes and we get other types of modes that aren't interesting to us. But you can see that it does actually kind of reach the levels of the observations if you have a high enough magnetic field. And so this is for 1,000 GAUS, but the problem there is that it's a bit higher than you really expect to find on the surface of the sun. That maybe in a sunspot, but we're more interested in just the quiet sun in general.
So it's a toroidal magnetic field, or?
Yeah. And so we also tried it with viscosity, and we get kind of similar results there that with small viscosity it doesn't do anything, and then it increases and eventually the modes disappear. But in this case, you see between 10 to the 8 and 10 to the 10 we get kind of higher phase speeds. But we have a viscosity estimate from the mixing line theory, and we end up with values that are substantially higher than that, so therefore in this case we could justify putting in a value that great. So between magnetic field and viscosity, some combination of the two is kind of enough to bump it up to the level of the observations. So we're pretty happy with that in terms of the linear model, that if we have the right combination of things, we don't think the Coriolis source does all that much, but it could contribute a little bit. But between the shear gradient with these 3 extra factors, it's enough to explain the observations. And that's what I said here. And so really now that we've done all this with the linear model, we'd be interested in seeing what the nonlinear model looks like, because we obviously want to have something that's kind of more realistic with the actual sun, but the problem is it's harder in that case, and I'm not really sure how to do this to actually link it to this shear gradient, because that's our whole theory, was that the shear gradient was causing this. And in the linear model, it's nice and easy to have that shear gradient term and stick it in there, and you have the velocity that you want. But for the nonlinear model, it's not really so easy, and so I would appreciate any kind of advice on how best to model this and still keep the same problem that we're interested in.
Yep. Thank you, Professor. Questions? Maybe first related to the last thing you said. I mean, nonlinear models, is your concern that the shear should actually be part of the solution itself? Or why are you concerned about this?
I'm concerned with this because, I mean, it would be nice to reproduce it in any case, to have
As a
a model
result of
that reproduces the observations. But,
The shear. It will produce a shear, I mean.
or reproduces this wave.
Yeah. Right.
But-
Shear.
The thing is that I've been trying to show that the shear is causing this, and
Yes.
I don't know, that seems like it's hard to do with the nonlinear model, since you can't just put one in and have the other one appear. That you kind of need to hope that they both appear, and then can you really say that one's causing the other one? Or,
Yeah. And now, the fact that the Coriolis force does not seem to actually work, does it indicate that the suggestion of Busse, who was, I think, simply only relying on the effect of the Coriolis force, has problems? I mean, that's.
yeah.
I mean, his theory, I think, was. mean, there was some symmetry breaking between up and down and stuff like this.
Mm-hmm.
I mean, that's one should actually make contact with both the theory, because that was also a linear theory
Right.
based on the Coriolis attack. So it's sort of strange that.
Yeah, it is strange. I mean, we did get a bit of wave-like behavior, so I mean, it wasn't quite as dire as when we were looking at those other simulations where it looked like there was no wave at all, that it was just advection. That we still get kind of the wave solution, it's just that it's very slow. So I'm not sure that perhaps there is some modification you could make that, with the right combination of stuff, would produce kind of a higher speed. So.
Regarding the shear, I mean, the way that we have been implementing shear in other contexts is by adding like for example in connection with Struber's work, where we have shear in connection with driven turbulence, we just add a body force to the simulation. A body force that is proportional to the actual velocity minus some reference velocity. So whenever there is actually a mean flow which is close to the anticipated shear flow, then this additional body force will be zero.
Right.
And once you have a departure from this, the body force will push it back to this reference flow on a certain time scale. So then the 1 over tau times the difference between the target velocity and the actual velocity. So that may be a useful concept as well.
So if you kind of average over time scales which are larger than the time it takes to relax,
right,
you will see the shear profile.
Okay.
On the other hand, in an instantaneous snapshot, you will see some fluctuation sitting on top of the shear profile.
Okay. Right.
And I think the best way to make progress is also to make exact contact with the linear theory, to reproduce the linear theory with the principle first. I think that should be the first target. Maybe we'll be able to achieve this here during the meeting. Other questions?
The shear flow be stable, or did you there's no instability for
I'm not sure because it's obtained from Hughes analogy, so obviously they're doing some kind of averaging, and they end up with this value at the end, but I couldn't say for sure what timescale that should be on.
I mean, that's an interesting question, of course, and it's has much broader impact. I mean, you are of course looking at a system which is already unstable because of convection. So if you were to do an instability analysis, and which you do all the time, you find imaginary positive eigenvalues, which means that it will grow.
Yeah.
And if he asks the question if it's stable or not, you would say, of course it's unstable, because it's convection. Now, then of course you can say, actually it's a departure from convection. So what kind of problem is that then? That would mean that you have to average over the flow. And then we ask, is the average of the flow stable? And that actually means that you have to develop, first of all, a mean field theory for the flow, which of course we know how that works, because that has to do with the lambda effect, which models the Reynolds stresses, the effect of the Reynolds stresses on to the flow. And so that produces, of course, the difference rotation with the lambda effect, according to mean field language. And then you will ask the question, so what about those mean field equations? Are they stable or not? And I think then one is back in a trap again, because consider this the problem without differentiation. Just take an ordinary convection flow. And Boris is not looking, but Boris is sometimes doing convection, of course. So suppose you do convection and you average this, of course you would get zero, basically. Maybe you would get a small vertical velocity which goes upwards, I think, because of mass conservation. So that would be the average solution, and you will do a stability analysis. So what do you think your eigenvalues will be? Will they be stable, or will they be close to marginal? Or will they be positive? And so this problem has been done actually in the literature, some 10 years ago and even before that. And some people found, using mixing length models, that it was actually unstable. Other people found that it was close to marginal. And I believe it's just a question of how accurate your mean field theory is, and it should really be marginal. But it really is very much a philosophical question, therefore. And therefore I was saying your question is very interesting, because there's a simple answer, which means it's unstable. There's a more complicated one, which means it should be marginally stable or marginally unstable. And in the presence of the shear, I think we really don't know. We have to trust the accuracy of mean field theory. So,
But you could check it with the computer simulator, right? Then you should get some answer.
yeah, right. And I think it basically will then, in the end, tell us that the mean field theory was not suitable for asking this kind of question. It's too complicated a question to be addressed by mean field theory at the simple level that we have available here. Yeah. Any other questions? Okay, so if that's not the case, then let's thank Christina.